Okay, everybody okay. First, let's introduce the jury first. I'm the chair of the jury. Actually, I retired from the first just 2 years. So I'm the jury, the chairman of the jury. Thanks for that.
I'm from D101 PF3.
Don't wait. Very well.
Hi everyone, my name is Charming Paul from National Central University.
From Academic.
Okay. So the student was introduced yourself. First, the reporter.
We're team the class. I'm the captain of the team. This is Wang Yan, Zheng Minhong, Lin Xueming, and Mo Guan.
Next, the opponent.
Okay, so I'm the leader of Ridiculous, and I'm Shaming. This is Li Yan, this is Yan Sanhong, this is Xiang, and this is Xie Xiaoqian.
Okay. Reviewer.
Hello everyone, I'm the leader of Team GWP, and I'm Hong Yubo, and he's Hong Yubao, and he's Qiu Songhan, and he's Yu Dayou, and he's
Observer.
I'm the captain on all languages of Taipei here. This is Stephen Peng, Radio, Daniel Lee, and Simon Tio.
Okay. We're trying to keep the time going on time. Okay. First, the opponent challenge the reporter for the property.
14? The challenge number
14.
14. Yeah.
You have 1 minute per speaker. Reject.
And then number 2, the challenge number 2.
You have 1 minute.
Reject.
Wow.
We would like to challenge problem number 6, dripping faucet.
Okay.
Reject.
After three, you have, what's the rule? Huh? Oh, the problem should be added.
Oh,
You should add some problem on it, because after 3 problems have been rejected, you can add more problem on it. Okay.
I think the rule is that if the problem we can challenge is necessarily 5, then we can add the problem. But
Oh, 5.
I'm not sure if I can add the problem now.
5 or 3? 5. Okay. Then that's fine.
And so we would like to challenge problem number 15, boiling ball.
We accept.
The opponent has 5 minutes to prepare. Write down the name who will present your team. Who will present your team.
statement. Strike the side of a metal ball containing some water. You can hear a characteristic sound. Sound changes when the water in the ball is moving. Explain and investigate the phenomenon. Let's hear the sound. So the sound would change with respect to time. I couldn't do the video. So our key questions are: why does the sound change after the ball is filled with some water? How does the frequency change while the water is moving in the ball? And what motions can we consider? So this is the structure of our research. First, we'll consider the static state when the ball is not moving, and we will explain why the natural frequency and the frequency when the ball is filled with some water is as it is. And then we'll consider the dynamic case with rotational and translational simple harmonic movement. So first is a briefing of our reference. We use AP fringe theory, which considers a cylindrical container, and it is partially filled with water. It is originally assumed to the static case. So to understand the cylindrical harmonics, we'll consider a simpler case, which is the mass on a spring. We can see that the energy can be written in this form with one proportional to the displacement squared and one proportional to the velocity squared. As we know, the angular velocity can be written as the square root of k over m. And generally, for a system energy written in the form of bx squared plus ax dot squared, we can obtain the angular frequency to be b over a square root. And with the ball's kinetic and potential energy, we also have to consider the kinetic energy of water. In the paper, they describe the kinetic energy of water to be in this form. And so if we know the distribution of water, we can know the kinetic energy of water and thus know the frequency of the whole system shown in this graph. So first we'll have to know what the natural frequency of the ball is. And we'll analyze the audio data to get the frequency plot using Welch's method. This is the frequency plot. We first have to know if the striking height is a parameter for the frequency. And after comparing the frequency plots and comparing the peaks, we concluded that the striking height isn't a parameter that affects the frequency. Next, we consider different nodal point and nodal ring amounts and how it affects the frequency. And as we show that the frequency is inside the range of theoretical prediction. Next is for different water level and how that changes the frequency of the ball. For different frequencies, we can use the kinetic energy formula as before and obtain the expression for the ball's frequency. And we can see that the experimental results match the theoretical predictions. And the d is the distance from the upper edge. So we can see that if we have more water, which means d is decreasing, the frequency decreases. This is like adding weight to the harmonical oscillator and the frequency drops, which is intuitively true. Next, we want to consider the ball in motion. We'll consider these three types of motion: coaxial rotational motion, translational simple harmonic motion, and observations regarding tilting. First is the rotational ball. We put the ball on the rotational platform and use a controllable motor to control a constant angular velocity. And we use a hitting mechanism to constantly hit the ball. We can obtain the water distribution using simple mechanics and obtain that there is a paraboloidal form of the water surface. And using the original plot for the kinetic energy of the water, we can obtain the formula for the ball in different angular velocities. And this is the graph. And we can compare our experimental results with different rotational velocity and plot it. And we obtain about 2% of error between these experimental and theoretical results. For next, we want to consider a case where the ball is actually emitting a welding sound, or the sound that is changing with respect to time. So we consider simple harmonic motion using a crankshaft mechanism, and we attach the ball to the end of the rod. I will try to play the video again. As you guys can hear, the sound changes with the time, and it sounds periodic, and it also looks periodic on the frequency plot. So next, we want to investigate this phenomenon. First, we have to consider the water distribution as before, and we concluded that there are 3 types of motion that are added together to create the water distribution. First is the instantaneous tilt due to the acceleration, and the forced harmonic oscillation, and the transient turn, which is oscillating at the water's original sloshing frequency. And after numerically integrating the DKL over the whole water surface, we can numerically obtain the frequency respect to time. And we can see that there is a decreasing frequency change amplitude and a periodic frequency change. And for different simple harmonic motion frequencies, we obtain the frequency plot. And together with the theoretical results, we compared these, and we find that the amplitude increases as the frequency increases. And this is because that the sloshing frequency, after we measured in the theory, it is about 3.7 hertz. So for all of the simple harmonic motion frequency we measured, all of them are lower than the sloshing frequency. So the higher the simple harmonic motion frequency, the closer it is to the natural frequency of the water motion, and thus creating a higher amplitude of sound change. So we also plot the frequency change period with respect to simple harmonic frequency. And we found that for the middle case, which is when the simple harmonic frequency is about 2 hertz, the simulation and the experimental data didn't match. And we think that this is because of the force and tilt term are decreasing dramatically when the detuning is large, meaning when the sloshing frequency and the driving frequency is largely apart, these terms would be small, but these terms were the dominant term before. So we have to consider the natural oscillation of the water. And the natural oscillation frequency is within the range that we observe in the experimental data. So we concluded that these oscillations are due to the natural water surface oscillation. And next is some observation regarding the instantaneous tilt of the This is a qualitative observation. So first we filled the bowl with some water, and then we hit it, and we can observe the frequency. When we instantaneously tilt it, it first goes up and then goes back. And we think that this is because of the unity of motion between the ball and the water. When the ball is originally stable, when you hit it, it is in line with the water and then oscillates. But when you tilt it, the water moves and breaks the unity with the ball's oscillation. After some time, the ball and the water re-establish their union of motion and thus lowering the frequency. And we think that this might cause that we need to have time-dependent correction to gamma 1 and gamma 2. So for conclusion, we established a physical model for water distribution change leads to kinetic energy change and thus creating a change in frequency. And we explained the sound of the welding. And for natural frequency, we matched the theory with the experimental results. And in frequency with static water, we also established a connection. With rotating water, we established a 2% error. And in simple harmonic motion using the water distribution, we were able to explain the amplitude and period of the sound. And at last, we were able to qualitatively predict how we might need to change the DKL that is established in AP French's theory to allow to explain the tilting results. Thank you.
Okay. Question from the opponent.
Okay, can I see your page 13?
13.
So why are these dots connected? Is there any physical meaning of it?
You're right. This shouldn't be a continuous line.
Okay, so
Because the nodal point should be a fixed, should be an integer amount.
okay, next question. How do you strike the dot?
I use a hitting mechanism like this.
Oh, okay. And I want to see your page 22.
22.
What is the unit of this graph? Well, I literally cannot
Oh yeah,
see the
yes.
unit.
Sorry, this is the frequency spectrum. This is the frequency, and this is time.
So how many frequencies do you acquire in the experiment?
What do you mean?
How many frequencies? Like, is there only one peak or many peaks?
There are many peaks, and we took the base peak.
And have you done any further analysis on the higher peak?
No, we consider the lowest peak.
And so you are not sure about if the higher peak is as the integer times of the lower peak.
It should be the overtone of the lower peaks.
So you didn't verify it, but you know it should be.
Yes, because the base tone should be the dominant term.
Okay, and I want to look at the page 24. How to verify your machine can conduct SHM?
Okay, we use tracker to measure the
Okay, maybe I think we should talk about it in the
discussion.
Okay.
Prepare for the opponent.
15. So first of all, let's purify the problem statement. When you strike the side of the metal ball containing some water, you can hear a characteristic sound. The sound changes when the water ball is moving. Explain and investigate the phenomenon. So this is the main focus that I want to underscore, is that the relevance between the motion of the water and the sound. Also, I want to ask a key question is what caused this? And I think the reporter has answered in the theory, but I would like to discuss more about it. And let's take a look at the general pros and cons. The reporter had a clear explanation of theory and cognitively illuminated the phenomenon and investigated several variables according to the problem statement. Clear illustration in data analysis. Nonetheless, there are still some areas for improvement, like filling the line with no reason, but maybe has reason, and I will inquire him later. And a clear unit, yes, just as I mentioned. And I think I will directly discuss with the opponent now.
Okay.
Can you turn to the page that you derived the correlation between the frequency and the kinetic energy?
Okay. Here.
Yes, it's a previous page.
This one.
Yes. So, this is the frequency.
This is the angular.
What did you say?
I said that this is the angular frequency of this system.
Okay, and I want to see the next page. So I think you skipped this part a little too fast. Can you
Yeah,
explain?
I can explain this. So, for a cylindrical container, we can see that the closer to the upper edge, the higher the displacement. So thus, there should be a higher kinetic energy. And the closer to the walls, because it's closer to the walls, the water will have more union with the container and thus have more kinetic energy. And this explains it.
Okay, so what is the shape of your ball?
Cylindrical.
Cylindrical. And did you do any further fundamental measurements of it?
We measure the radius, the height, the thickness.
Okay, so where's the data?
Oh, I didn't put it in this. I should include it in the slide.
Okay, so what are these fundamental, like length or other factors, affect the phenomenon? How?
So, first of all, I want to turn to my appendix because that includes.
You have appendix, that's great.
That has the kinetic energy and potential energy of the ball. The kinetic energy takes this form, and the potential energy takes this form. And F of C
I want to ask first, what is this fraction? Is this the result of the integration?
Yeah, this is a result due to.
So can you derive it on maybe can you use the I will ask the jury if you can use the blackboard.
Sure.
Okay, so can the reporter use the blackboard? Okay, so
Can I just use the just open the reference? This is the derivation. Kinetic energy follows this derivation as so, and the potential energy uses this simple elemental analysis.
oh, okay. So I just want to show if this is the integration results, and now I know this is the integration results. So let's move on to the next question. So you mentioned that the way you strike the ball did not affect the frequency. Is that true?
Yes.
So how do you define strike with how much force? Because your machine can apply different magnitude of force And what is strike?
Uh,
What is the definition of strike?
strike is a quick contact and then leave.
What is quick?
So, there is no observable time that I can see that the ruler is contacting on the ball. Do you know what I mean?
I guess so. So when the force reduced, when the force reduced to a value,
Yeah.
the phenomenon cannot be observed anymore. And have you investigated the critical value?
What do you mean?
I mean, when the strike force is lower than the critical value, and the phenomenon cannot be observed anymore. So did you inquire into this?
You mean when the sound cannot be heard?
Yes.
I don't think that is it's worth investigating because the point is that we want to hear the sound of these certain balls.
Oh, okay. And I remember in the good question I have asked you about how to verify your machine can do the simple harmonic.
Yeah, sure.
Oh,
Okay.
explain that.
So for periodic motion, we use the crankshaft mechanism, and for long crankshaft, which is when the shaft is longer than the crank, it can be approximated as simple harmonic motion. If you want, I can show it on the left.
So do you mean because it is the projection of the circular motion, so it is a simple harmonic motion? Oh,
It's not the simple projection, but it can be approximated when in this case.
okay. So I want to take a look at the page 33.
33. Yes.
So, can you explain why is the amplitude correlated to the frequency?
Okay, so I have to go to this page. So you can see that there are three terms. If you want, I can tell you how these terms came to be, but just for simplification.
You can brief, say it brief.
Okay. So when the forcing is larger, the forcing frequency is larger, so this term would be larger. And then for this term would also be larger, so this decreases, and this decreases, and this increases. And for this term, there is no but this is smaller than this.
And are these, did you derive these or this
Yeah, I
from
did.
reference?
This is derived.
Oh, you derived those, okay. And for and what do you think is mainly vibrating in this?
Both the ball and the water.
How about the air? What motivates the vibration of the air? Is it the water or the ball? The ball.
I mean, the water is moving with the ball, so the ball is in contact with the air, and plus the air has sound because the air that is closer to the ball is vibrating with the ball in the boundary layer.
Okay, so what if the air is affected by the water wave?
What do you mean?
There's wave on the surface of the water, right? Is that observed in your experiment?
What do you mean?
Did you observe any wave on the surface of the water in your experiment?
It is included in this term.
I mean in the experiment.
Yeah, I did.
Oh, you observed that. So you mean you can use this equation to describe the effect from it?
Yeah, this is the Basel function, and it describes the most simple dipole mode of the water surface.
Okay. So you do the simple harmonic motion experiment. So what is the relevance between the frequency of the simple harmonic motion and the frequency of the sound?
The frequency of the sound. Yeah.
The correlation.
Yeah. So after the water is doing this motion, can I turn to that slide? So the water is in something like this, right? So the water has this basically tilting have a larger displacement than the lower part.
So wait, are there any relevance between the frequency of the SHM and the frequency of the sound?
Yes.
Okay, so what is it?
The larger frequency of the simple harmonic motion causes the larger amplitude of the tilting and sloshing amplitude, which gives a larger decrease in the frequency.
And is there any quantitative results for it?
Yeah.
Can you show me?
We didn't quantify the amplitude because due to the resolution of the frequency part, but we can see that when the simple harmonic motion frequency increases, the amplitude increases.
So what do you think is this very small frequency?
This is the low noise.
Low noise,
This
which
is
is
the
caused by the machine.
No, it's just environmental noise is all low frequency.
Okay, and why do you think the problem statement they mentioned it have to use the water? Why should we use water? Is there any characteristic of water that that is the reason why we should have to use water?
You mean
Some characteristics of water cause this phenomenon.
as opposed to other liquids?
Yes, I'm asking this.
Okay, so I think that this experimental is conductable in different liquids, but like if it is ethanol, it might evaporate and the volume doesn't stay constant. And water is also incompressible, which is easier to manipulate, and
I get it. So
it has higher mass.
can I see your observation here?
For this experiment,
In the first.
the first.
Okay, in the first question you told me that the ball is cylindrical.
Oh, this is just for easier.
And can you show me the cylindrical ball?
Yeah. Let me see here. This is here. It's cylindrical.
Okay, so is there any theory to explain the ball that is not cylindrical?
Yes, I believe there is for.
And did you inquire into this?
No, we considered the cylindrical case due to its symmetry and easier to explain.
Okay. I want to see your movement.
Which one? This one?
Okay, maybe the one with video. Maybe I can rewatch the video.
This one.
Yeah, yes, I want to watch it. But I see the machine not only caused the SHM on this direction, but also that the ball have a vertical pendulum. I think I saw that. Did you saw that?
Wait, let me see it again. I
Yes,
did
a
not.
pendulum on the vertical direction that caused extra vibration to the ball.
I did not see it.
You didn't see it?
I
Okay, that's okay.
summarize.
So in the discussion, we talk about the frequency of the different experiments and talk about three types of motion. So the opponents do a very well research on the different types of motion that affect the frequency. However, the reporter ignored the shape of the ball and also ignored the higher peak of the sound, which is such a pity. And and that is what I expect to see. And also we talk about the theory, and the theory I think that is a very full mathematics. And also we clarify some definition, and this discussion helps me understand this topic more comprehensive. And I want to thank the reporter. Thank you.
Honorable
Can you please turn to page 38?
38.
So what these two balls you can conduct in your experience difference? Like two balls will follow the ball size impact on the frequency you heard.
I think the ball size will impact the height of the water, which definitely will impact the frequency.
Like how? Like a higher frequency or lower frequency?
I think the graph is lower. In the graph, you have the graph. I saw it.
Like, but the graph in his experiment does not maintain the same mass of water.
I'm not sure.
Did you maintain the mass of water when you conduct different ball shapes? Like you strike the balls. You have two shapes of ball, right? The mass inside the water mass inside your ball is the same.
No.
No. So you didn't compare these two balls. You separated.
Yeah.
Okay. And for another one, in your experiment setup, I think that the place you hit is not always the same. Do you think that will affect?
No, because we already conducted and we verified that the strike impact is in
So you don't think that will affect?
Yeah.
How about you?
Do you mean
The position you
the
hit,
position on the
like side or
vertical?
vertical?
For the side. The side. I think it doesn't affect because it is the ball is vertical.
Okay. And you say that you consider the lowest peak in your frequency.
Yeah.
Did you consider any environmental sound that was here at the lowest frequency? So have you had the background sound
Yeah.
to compare with? Can you show me the
We,
background?
we did the experiment.
Okay, when you find, I want to ask, instead of finding the lowest peak,
Okay.
why did you think that you should consider the highest?
Yes, because the higher peak can help him to verify if this is the peak that we want instead of like some noise.
Okay, and can you please say that, how did you measure the difference between the background sound and your experience?
We measured a blank sound.
Like, do you have the graph and to show me?
Oh,
So this is the background sound?
the background sound should be the peaks where the sound doesn't decay. So you can see like here.
So why there isn't any?
So this doesn't have any.
So no background sound?
It's not noticeable here.
Not noticeable? Okay, and how many times did you repeat your experiment? Like every time the water distribution was.
Time's up.
Honorable judges and worthy contestants, this is the reviewer reviewing the question wearing balls. This is the problem statement, and the reporter focused on the motion and the sound relationship. So this is a summary of the report. The phenomena included is the striking the metal ball, a characteristic sound can be heard. And the theory they include is an AP fringe, a theory, and the kinetic energy of water. Experiment, they conducted a lot of experiments, including about the natural frequency, the water level, different size of the ball, and also investigate the amplitude increases as the frequency increases. So here are the pros and cons about the reporters. Reporters presented a detailed theory regarding static phase motion, and while a wide range of consideration is provided. But for the cons part, for the SHM model and video, the reporters are hitting it with pen, and lacks of notation in his presentation since he used a lot of reference. It is not understandable. And as for the opponents, the plus is that he detailed consideration of initial conditions, and he clarified on many definitions about the presentations. And he can also consider a striking as the ball is moving. So this is the discussion part. The opponent thinks that the shape of the ball will affect, and the reporter says that they use a cylindrical ball and a metal ball. And as for the kinetic energy of ball relationship with frequency, and how do you get it from integration results, and the reporter gives references derivation on research paper. And the opponent thinks that he wants to define the strike and quick in the reporter's presentation, and the reporter answers that the quick contact and movement, which is also understandable. And the opponent also asks that how to verify the machine to make sure it does SHM motion. And the reporter says that long crankshaft mechanism can do it. So opponent also asks what's about the vibrating and the wave on the surface water. The reporter answered that the ball in contact with the water, and they did observe it. So the opponent also thinks that why should we use water, why we don't consider another liquid? Is there any characteristic of water that causes this phenomenon? The reporter says that this experiment is able to conduct it in different liquids, but they didn't do it. So the opponent also thinks the height of water matters, but the reporter doesn't think so. So we think that on page 38, what will the ball size impact on the frequency? The volume of the ball, how will that impact? And the opponent thinks that the size does not affect since ball is symmetrical and is aligned with the reporters. But in our opinion, there also will be some non-symmetrical water distribution exhibits. So this is the missing parts. The background noise clarification is vague in his presentation, and any standing wave occur in his experiment is not discussed. And what will affect the natural frequency or what will affect the K is not discussed in his presentation either. And the definition of natural frequency is whether an empty ball and you strike it, or an empty ball not vibrating, you strike it. He didn't define what's the natural frequency there. And as I mentioned before, non-symmetrical water distribution may occur as you rotate the balls. And you can't make sure that when you rotate the ball, the water distribution is always the same. That's all. Thank you.
Okay. Please stand up. Question from the jury.
So this is my concluding remark. For my own contribution, we found out that the frequency is related to the energy ratio. And we clarified that by water distribution, we can know the kinetic energy of the water and thus know the frequency of the ball. For short questions, I was asked how many peaks that I consider and the verifications on simple harmonic motion. For this, I said that the long crankshaft can be approximated as simple harmonic motion. And for the how many peaks that I considered the bass tone due to its larger amplitude. For the discussion, I was asked to define quick, and I didn't give an answer. Verification on the simple harmonic motion, I verified it with him. And the air vibration, I think that it is the cause of the sound. And the relation between the frequency and simple harmonic motion. I told him. And next, we also derived the potential energy and kinetic energy of the ball. We found the sound source. And I was asked, why did we use water for the experiment? And I answered. And for the reviewer, I was asked, what is the difference if I didn't use a cylindrical bowl? And also, does the strike height vary the sound? And for higher frequency peaks or background noise? And also the water distribution when it's not symmetric. And that's all.
Question for the jury. Go ahead. I really don't understand what's the problem. So tell me the first question. What's the nature frequency of the water in this case?
The natural frequency of water
Yes.
is the sloshing frequency.
I'm asking the frequency. I'm not asking the definition.
3.711 hertz.
People,
3.7 hertz.
can you hear it?
What?
Can you hear it? 3.7 hertz.
The ball's frequency or the water's frequency?
We are discussing the.
Natural frequency of the ball. It's
No, I'm not. What's the problem? The problem is measuring the sound, right?
Yeah.
So what's the frequency of the sound?
1,200 hertz.
Okay.
I have a follow-up question. So the sound mainly comes from the water or mainly comes from the ball?
Ball.
And in this year we only talk about water. We talk about ball.
I also calculated the kinetic and potential energy, but it's the water that changes the frequency. So there is a base tone, and then the water is effectively the added weight on the ball, so it influences the frequency.
You compare the frequency from an empty ball.
Yes.
What's the difference?
Yes.
The frequency is lower. So the
How much? No, how much?
so this one, so we can see that when D is highest, this means that it is empty, and when D is 0, it means that it's full. So we can see that the frequency drops.
What's the meaning of the x-axis and the meaning of the y-axis?
Okay, so D is the proximity of the water surface from the higher edge.
Okay. So what's the meaning of this one? Meaning when the water is full, the frequency will goes down.
Yeah.
The other question goes to which one? 17. Okay. When you discuss the rotation,
Yeah.
did you fix the rotation frequency?
Yes.
So that shape is fixed, right?
Yes.
But can you talk about the standard simple harmonic oscillation?
Yeah.
You discussed the slope right there, right? But the slope keep changing.
Yeah, it keeps changing.
So the frequency,
Keeps changing.
did you hear it?
Yes.
Did you record it?
Yes. I can play it now.
Okay.
Yeah. Play it. No sound. No sound.
Oh, my next question. Can you point out which frequency is related to which time?
What?
Because harmonic oscillation is going from one point to the other point.
Yeah.
Can you point out back sound is at which point? Which position?
Sure. So, in this case, the oscillation frequency is 2.6 hertz. So
In this case,
Yeah.
you have a ball.
Yes.
It keeps moving, right?
Yes. Yeah.
When you hit it,
Yes.
and beginning and middle of the ring, or at the end, the frequency should be
Different.
patient for the opponent.
Okay.
How do you measure strike? Quick. How quick the strike? How did you measure? For those close. Better. Time's up. Let's go. Okay, for the reporter, seven, 6, 4, 7, 7. For the opponent, 8, 7, 5, 7, 7. For the reviewer, 7, 6, 5, 6, 7. Do you have any comment?
Well, to me, I see this is a very equivalent, simple equivalent symbolic motion, and I think the reviewer, at least you should be able to use a very simple equation to tell us the equivalent variable